Welcome back, everyone. Good to see you. Some of us are still on fall break, but maybe they're watching the recorded version, which is fine. Today we're going to specifically review Chapter 3, but I did set up a little bit of the review for Exam 2, which we've kind of done. So this is sort of a second half review, right? We did Chapter 2 review, and I'll highlight that. So I just wanted to show sort of backwards. I've got the review for Exam 2, which we'll be looking at completely on Monday. Let's open it up. One thing I did add in here from my trig class, I've got a video on how to construct the unit circle sort of from memory. And just thinking of counting from 1, 2, 3, you'll be able to do it. So it's in there. If you want to, it might be good to take a look at a refresher on that part. And then I have just the general Chapter 2 review, or Exam 2 review that has the answers, the questions and the answers right underneath it. I guess that's up there. Oh, and then there's this link to the department's website, which has review stuff for all the stuff, and they've got some videos on there, so you can check it out. They have some useful stuff there. So I just want to show you that one. Right above that is what we did for Chapter 2.4 to 2.8. I'll probably update that a little bit. In fact, I just saw the instructor that's before us. She teaches, see what, this is 265. I think hers is 267, which is just a different flavor of Calc 1, and she's got a sheet with all the derivatives. I thought, that's a good idea. So I'll post this. I'm going to make one change to the product rule because I do it backwards from how everyone else does it, because then that makes remembering the quotient rule a little easier. So I'll just do a little edit for that, but I'll put that up there as well. So what we'll do is we'll focus on the review for most of Chapter 3. We're not doing 3.4 or 3.6 because we didn't cover those. And so there is a document which I'm going to use, a Word document instead of a PowerPoint, because it's a little easier to work through, so we can work through some problems together. And then, so there's a content review, and then there's just the Chapter 3 portion of the Exam 2 review. And what I did on that, I edited a little bit, took out the Chapter 2, and took out all the answers, so that you could kind of just do it without the answers there. If you want the answers, it's in the full review. I didn't take them out from there, but just was hoping that it would work. So in the content one we're going to work on today, what I've done is I've highlighted, I think I can just maximize this. Let's go with blue. I've highlighted the important things that we need to go over, but actually first I didn't write this down, but verbally, I do have the exam, and so I've reviewed it. It's much like last time. It's 8 questions, multiple choice, 3 questions, free response, so essay answer. There are 4 of the multiple choice are from Chapter 2, 4 are from Chapter 4, 4 are from Chapter 3. If I remember how to count. Okay, so, and we'll take a look at some of those. From the free response, 2 are from Chapter 2, 1 is from Chapter 3. So the things you want to be sure from Chapter 3, since we'll focus on the Chapter 3, know how to do logarithmic differentiation. You know everything, but these things especially. Know how to expand logs to take its derivative, because if they give us a log with a bunch of stuff, we expand it outright, and it's easier to do it. So know how to do that. Know how to take the derivative of an inverse trig. So we're going to highlight that in a question. And know how to take the derivative using Theorem 7. And I've got the Theorem 7 in here. It's from 3.2. We came across, I think it's 3.2. Yeah, 3.2. So we'll do a problem with that. And then also know how to apply L'Hopital's rule. So nothing too extreme, but know how to do those. And again, be able to sort of show your work on all of them. Again, on the multiple choice, you don't have to. You just have to get to the right answer. But feel comfortable enough to kind of at least get all of these started. But if you can do those, you'll just be fine. Monday, I'll highlight the parts from Chapter 2 that are the most critical. And then we'll go from there. So let me make this a little bit bigger. And so these are things I took out of the PowerPoints, which I took out of the textbook. So there's these boxes here. So just an overall review. 3.1 was on exponentials. So there we had the rules for exponential. And again, we won't have a question that directly asks us to apply it, but we might need to apply these things when we're taking derivatives and doing the algebra. Okay, so that's kind of background. And then the properties of the natural exponential function, you can get that from looking at the graph, because a natural exponential is kind of a J shape up if it's an increasing one, right? And so over at negative infinity, the function is going to 0. At positive infinity, it's going to infinity. Y is going to infinity. So that's kind of helpful when we start talking about limits, because some of the stuff we're going to do will involve limits. And L'Hopital's rule, right, involves limits, at least being able to apply it. And so e to the x, if the x goes towards positive infinity, y will go towards positive infinity. If the x is going towards negative infinity, the function goes towards 0. Okay, and again, you can see that from the graph. So the other skill I highly recommend as you're taking the test, if you can. At least, or maybe while you're preparing, take a look at graphs so that they're in your mind. So maybe when a question comes up, you can sort of see how they look. If you're not quite sure, go ahead and graph it. It oftentimes tells us a lot of questions. Why is this going to infinity? Well, just because the graph's going up to infinity. It looks like it is. Or why is it going to 2? And you'll see the graph goes to 2. It helps build that confidence. So nothing directly from here, but again, stuff we will probably be using. Inverse functions, know how to find an inverse. And again, when I went through this, I sort of switched steps 2 and 3. I tend to switch my x and y variables first. And then I solve for y, but either way. So they solve and then they switch them, but that'll work. And then this one, Theorem 7, this theorem doesn't allow us to find the inverse, but it does allow us to find a particular value in an inverse if we have enough information. So we'll work through one of these problems. They're kind of a little tricky, but kind of get down how to work through them. Okay. And then we had 3.3, and again, this is all in Canvas, so you can download this. I put it in a Word file so that the pictures, you can resize them if you want to make them smaller and like get it all on one page or something and have it while you're working. But these are the kind of things that if you know that, like I said, at a minimum, if you know this, you'll be fine on the test. It's not that there isn't other things we covered, but I tried to narrow it down. Let's just focus on what we're going to really need. So the derivatives of exponentials and logarithms. So we first talked about log base a of x, right? And that's 1 over x times the natural log of a. I didn't put in here the derivative of the natural log because it is just a special case. So if we've got the natural log, when we take its derivative, it's 1 over x, and the base here of a natural log is e, so it's the natural log of e, but what's the natural log of e? It's 1. So as long as you remember that, you don't really need to remember 2 special different cases for natural log and any other log. As long as you know the main one for logarithms right here, you can come up and say, oh yeah, that's just 1, so that's why we don't put it there. It's just 1 over x when we do it. So it's a little bit easier when we have the natural log. But just remember logarithms, 1 over the input times the natural log of the base. When we get to any exponentials, again, I didn't put a special case for e to the x, but you'll see that it really flows from here. Any exponential, in this case a to the x, is its own derivative times the natural log of the base. Okay? So you see it just like what happened. It's still got a to the x there, of course. It's always going to have that a to the x, but then it's got the natural log of a. When we have e to the x, the same rule follows. We get e to the x, and then we get the natural log of the base, but the natural log of the base is 1. So 1 times it sort of disappears. We never see it there. But I just want you to see you don't need to memorize a special rule. If you remember the base rule, it will be there, and you go, oh yeah, and just remember natural log of e is 1. So this is, right, and I guess up here we'll just say this is 1 over x. Remember, when we do this, we're going to use the chain rule too. So if the input, if the exponent or the thing in the logarithm is something other than just x, if it's 2x or x squared or something, we've got to use the chain rule on that, and we'll look at a couple examples. We'll do that. We need to be able to use logarithmic differentiation, and that's nothing overly difficult. It's just take the natural log of both sides, expand them out, and then you can find the derivatives. And then when you got the derivatives, you back substitute, because you're going to use implicit derivatives. You're going to have a derivative of y. You're going to have a y prime or dy dx, but you're also going to have it up here. So we substitute back in, and we'll get it. So we'll take a look at one of those. Again, the technique is not so hard. It's just that it's kind of this process that you have to have down. So we'll look at one of those. Inverse trig functions. So I've just got part of the unit circle. If you remember just this little quarter, you can reconstruct the rest of it, because all that changes are the signs on the x's and the y's, right, as it goes around. So we may need to use this from time to time, but at least if we have this, we should be able to create the rest. I did get a question, will we have a unit circle on the exam? And the department's feel is, you took a trig class, you should know how to construct a unit circle. I get the same thing in my trig class. They won't let me use a unit circle. I do a template, and that's where the video I showed, is I show them how to recreate that template and count through the various angles, both pi's or both radians and degrees, and then fill it in. And it's about the main part of it you can watch in about 10 minutes, unless I talk kind of slow, so I always do things like at double speed or 1.5 speed, so you can get through it in probably about 7 minutes, and then you'll know, you won't have to memorize the unit circle, you'll remember how to create it in a short period of time. Okay. These things we'll come back to. So this is when we're going to take the derivative of a inverse trig. We're not going to expect you to go through the process of doing it from scratch. We're going to kind of need to remember this. I'll just give you a hint. We don't have to remember any of the inverse ones. Of the reciprocal ones. So sine, cosine, and tangent, if you focus on those, you'll be fine. So just for the exam, focus on those basic ones. The other ones, again, they're in some of the homework, so we use those, but make sure you know sine, cosine, and tangent, what their derivatives are. They just are what they are. And if it helps to get some explanation of how it happens, look back at that lecture. That was, what was that? That was 3.5, and we went through and we developed the sine, inverse sine from it. I think we did the trig one, or the tangent one as well, but take a look at that video. Also, I'm going to keep office hours after class today. I have nothing better to do with my life, so why not? We'll just hang out. So anyway, if you have questions, come on and we'll go answer some things, any questions that you have. But again, we'll make sure that I've got 5 questions today. I want to make sure we get through those, and then L'Hopital's rule, which is not really his rule, it's really Bernoulli's. I just keep saying it's hard. Once I learned that, this first time I learned it, so it's kind of like, the guy stole it, and he gets all the credit. It's kind of like the story of my life too. Basically, we check the limit first. If it goes 0 over 0, then we can use it, or infinity over infinity. Yeah, I gave this idea to my department chair. 2 months later, he's got it. It's a district-wide project about his crazy idea. I go, don't you remember I told you about that? He goes, oh, you did? So, okay, well, it's going to be that way about it, huh? So, anyway, I mean, he put some research stuff behind it, but it was the same idea. So then what we do is we take the derivatives until we get something that gives us a limit that isn't infinity over infinity or 0 over 0. Now, one of them may still be infinity, or one may still be 0, but if the other one's not, then we arrive at an answer, right? It's only when they're both 0 or both infinity that we don't know what's going on. That's called an indeterminate form. And that's the review of everything we've done in Chapter 3. That's of importance, of major importance for next week. So let's take a look at this first question. And again, this is saying for the function that we're given a function, we're asked to find the derivative of the inverse function for a particular point. where we're given that c is equal to minus 9. In other words, they say find the inverse, the derivative of the inverse at c with c equals minus 9. So they're saying find the inverse at minus 9, the derivative. And the way we go about doing this, we're going to go back a little bit. And this is why I kind of put it in one document. I hope I don't give anyone motion sickness by going back and forth. But this is what we want to focus on. Okay? So we want to remember this. What is this saying? It's saying that the derivative of the inverse at a particular point, that's what the first part is, will be equal to 1 over the derivative of the initial function with the value of the inverse at that point plugged in. Okay, so there's two things that we really have to calculate. We have to calculate the derivative of the original function, and then we have to figure out what the value of the inverse function is at the point we're trying to get. Okay, and we're kind of going to have to do that. The way we do that is sort of working backwards. So we really use the original function. We never find the inverse function here. Someone asked me to do it, and I got lost for about 15 minutes. I go, wait, we can't. We don't have techniques to do that. So this is something you're going to want to remember. Again, we don't give you a formula sheet, but part of it is we want you to study hard enough that these kind of things are what you remember. And hopefully I'm making it evident that this is something that's important to remember. And you won't be sorry if you remember it next Wednesday. Okay, so we're going to come here. So what we're going to use, and I find it helpful for me to rewrite things multiple times. So the derivative of I'll just do it, c is equal to 1 over, because they're using c instead of a, the derivative of the original function with the inverse function's value at c plugged into it. Okay, so I've rewritten it. So okay, now I've got my plan of attack. I like to do the easier stuff first. I'm more comfortable taking a derivative at this point, so let me just take the derivative of the original function. So derivative of the original function, not the inverse function, comes from here. So derivative of 3x is 3. Derivative of 6x to the 15 comes down. 15 times 6 is like something like 90. And then we've got x, subtract 1 from the exponent, so instead of 15, it's now 14. So that's one thing we're going to need, right? What's the other thing? So we're getting pretty close here, right? We've got this part. So now we need to know what to plug into that derivative, and we're home free. This is the harder part of the whole thing. So what is f inverse of c? Well, they tell us, so we got to think of what is an inverse. So we know where does the input for an inverse come from? It's an output for an original function, right? And what will be the output for that inverse at that point? The input from that function, because the x and y's are just switching places. So what we have is negative 9 is a y value from the original function. We just need to know what the x value is, and then when we switch them around, we'll have our output. Okay, so that's all we've got. So negative 9 is a y value from the original function. So we get to write this, negative 9 is equal to the original function, 3x plus 6x to the 15. And all we got to do now is find x. This is where it seems really hard, but they usually give us something fairly easy. You see the coefficients 3 and 6? If you add them together, what do you get? 9. So what must x be so that we end up with 3 plus 6? 1, but actually should be negative 1 because we've got negative 9. So think, and all of these will be that way. Because if it was something else, I tell you, we can't take 15th roots, and this thing would be a mess to try to solve. We don't have techniques. We've never learned them in our algebra classes. But what we can see, and most of what they'll say is, oh, it's obvious x has to be -1. And these are odd, right? If you plug in -1, you get -3 plus -6, which is -9. It works. So that's actually all we need is one place that works. So what we've got is we've got that from the original function, there's a point -1, -9. So what we now know is that when we take our inverse function and we plug in -9, which is the output from the original, what's it going to be? It's going to be equal to the x value, because remember, the inverse function, you plug in a y value, you get the x value as an answer. It's all backwards. The original function, we plug in an x value, we get a y value. So this is from the original, this is the input, there's the output for the inverse. -9 is now the input. What's the output? -1. That's the hardest part of, and that, I mean, literally for me, I had to think through this before the class today. I go, how do I explain this? I can do it, but that's what we're doing, okay? And so where does this -1 go now, right? It goes in our function. We have that, let's switch colors. Let's go to lighter blue, I guess. So the derivative of the inverse at -9 is going to be equal to 1 over, well, we'll go ahead and just write it. This inverse function at what value? -1, right? Because what's in here, this is f inverse of -9. So we figured out what that answer is, right? This here tells us what to plug in. Well, what's the f inverse? It's up here. So we get that our answer is going to be 1 over 3 plus 90 -1 raised to the 14th power. And again, we're happy that they've got a number like 1 or -1, because raising something to the 14th power is going to, if it was like 2, even if it was 2, it would be a huge number. Calculators would probably blow up. But since it's just -1, it's an even exponent. So what does that mean the -1 becomes? +1. It's like you square it, it's always going to become positive. So it's +1. So +1 times 90 plus 3, 1 over 93. That's our answer. Okay. We did not find the inverse function. They didn't ask us to find the inverse function. They just asked us to find a particular value. You okay with that? Yes.
So, one more time, how did we get -1 for x?
What we did is we looked at the coefficients and noticed that 6 plus 3 gives us 9, but we need -9, so we need x to be a value, we need them to be multiplied by -1, and certainly -1 works on the 3, because they just plug in for x, that works. But it also works if you take -1 to the 15th, you still get -1. Now, had that been an even one, we wouldn't have been able to solve it. But trust me, they will give you ones that are solvable fairly easily by this way, because it's really just to show you that there are some special applications out there for derivatives. Somebody came across this, it's esoteric, maybe they were doing their graduate work or something, but I don't know the history of this, but someone came across it and it's useful. You don't have to find and that's what we use calculus for, is as we learn more and more math, a lot of times we're able to go back to things we weren't able to solve very easily or at all, and now we can solve them with some different techniques that work in special cases. Okay, so far so good? Okay. So that's the one with that special from 3.2. So again, understand how to do that, and that's the hardest part, is finding out what the output of it is. Again, once you look at it, but it's really kind of, because it's by inspection. You plug in that's the answer to the function. You'll see usually it's the coefficients will just line up. Okay, so we're asked to differentiate this. This doesn't look like too bad of a thing, x to some power, right? We just subtract 1 from the exponent. But what's the problem with this exponent? It's got a variable in it. And we haven't really talked about how to do that. We'd have to maybe do the chain rule, but here's a chain rule, and we don't know how to do this unless we use logarithmic differentiation. Because if we take a logarithm of that, what's it going to do? We got to take the exponent down, and now it's a product rule. So that's the only way to address these types. If we have an exponent, we've got a variable base and a variable exponent, the only way to do this is use logarithmic differentiation. So look for those. And so what we do is we sort of just take some liberties. Instead of f of x, we're going to write it as y equals x to the 6x. Okay? And notice it doesn't say use logarithmic differentiation, but that's the only way we can do it if we've got a variable to a variable power. So what we do is we just say, okay, let's take the natural log of both sides. We can do that. Why can we do it? Because natural logs are a one-to-one function. And as long as both y and x, as long as the inputs are positive, right, we can't put negatives in there. So there's some caveats, but so far this is really the only thing we can do with this. But it works as long as we do that. What does that give us? Well, it gives us the natural log of y. Let's use a logarithm rule. What can we do with this exponent? Move it down in front. So it's 6x times the natural log of x. And now we've got something we can differentiate. It doesn't maybe look a lot of fun, but we're going to have to use a product rule over here, and we're going to have to use implicit derivatives because we're taking the derivative of both y and x. Okay, so let's go ahead and do this. Let's take the derivative, and I'll just do it as d dx. That's sort of just a generic for take the derivative. And let me, it's the other nice thing about having a Word document, you get as much space as you want. So what's the derivative of natural log of y?
1 over y.
Excellent. So it's just the natural log of y, that's 1 over y. Since we took the derivative of a y, we have our marker dy dx. If you want, in the text sometimes we'll use just a y prime. I tend to lose y's and y primes, so I like having dy dx. So then we come to the other side and we're going to take a product rule. So we take the derivative of 6x first, right? I always take the first one first. So what's the derivative of 6x? So that's just going to be 6. Natural log of x, nothing happened to it. We didn't do anything. It's product rule stuff. And then we get a plus out of this. And then now we're going to take the derivative of the natural log of x. And what's the derivative of the natural log of x?
1 over x.
1 over x. And we have 6x in the top, because that just comes along for the ride. Is that kind of, so far are we okay?
Yeah.
Product rule. So let's clean this up a little bit. Our x's can cancel, right? X divided by x here, so we just have 6. 6 natural log of x, that's going to stay. Over here, what we want to solve for, the derivative that we're looking for is dy dx, right? We'll call it f prime. So what do we do with this 1 over y? Multiply both sides by y, so we can get rid of it. And then the last thing we're going to do is, right, we started off with what was y? Y is x 6x. So that on this side, we're going to have terms that only have x's in them. We won't have a y or anything else in them. So we're going to make this substitution when I rewrite it. So we're going to replace y, and this y is really times this whole thing. So we're going to find that our final answer is going to be, you could factor out a 6, I guess, but you know, the thing is on some of these, for multiple choice, you just have to be able to recognize the right answer and recognize that they may factor something out that you didn't, or maybe they didn't factor it and you did. You just have to be able to do that. And I think in most cases they would go something like this, And then what goes here, well, that's times y, but we're going to put in the version of y that y is really x to the 6x. And that kind of fits with what we think of a derivative of a exponential, right? It's its own derivative, so it shows up again. It sort of is, but then it's got this other stuff. We would have never probably been able to figure out this stuff on the inside. I wouldn't. I don't know, it'd be a mess. But it's kind of reassuring. And this is really just derivative of f of x, okay? So it's just kind of change it, put instead of function notation, y equals a thing, take the natural log of both sides. If you have, and then use logarithm rules to expand it out so it's something easier that we're just using either product rule or sum rules. Take the derivatives, simplify a little bit, and then back substitute for that y, right? Because we'll always have one, because you got natural log of y, it's always going to be 1 over y, dy dx, and then when you get it to the other side, it's just y, so you'll always see that original thing there. And that's because that's what we use it primarily for, is when we've got a variable base and a variable exponent. You okay with that? Good. So now we're going to do, oh good, I think we're just right on time. Let me just give myself enough room here. Yeah, that's fine. So this is similar, except that this problem already has a logarithm in it, but we're going to see, so we might be tempted to just try the chain rule type thing, but oh wow, that's really messy on the inside. So before we start finding the derivative, what we're going to want to do is expand it out, and then we'll find that our work is much easier. We don't have to use a triple chain rule, product rule thing, okay? So first step is let's just use our algebra on f of x. So we're going to expand out. And what you have to see is that there are 3 things being multiplied, right? So we've got this times this times this. When we expand a logarithm, what does multiplication become in the expanded form? Addition. Excellent. So, and that's what's going to make this easier to work with. So this now becomes natural log of x to the 6 plus natural log of x plus 5 to the 9th plus natural log of x to the 3rd plus 1 raised to the 10th. And then what other logarithm law can we use? The exponents. So take the exponents, they become multiplication in front, which was really nice because when we take a derivative, it's just a constant multiplier, just comes along for the ride. We don't even have to deal with exponents anymore. So our next step is to say, okay, one more logarithm rule. 6 comes in front, so 6 natural log of x. Isn't that just going to be a nice, easy 1 over x? Yeah. This one, the 9 comes down in front. Natural log of x plus 5. Another nice, easy derivative to take. And this one, the 10 comes down. This one's going to be the more complicated one because we've got an x cubed inside, so we will have to use the chain rule on this one. We always use the chain rule, but this one has something that comes off of it. Okay, so far we good? Again, this is all just algebra expanded out. Let's take its derivative. So the derivative of 6 natural log of x is 1 over x. So the 6 is in the numerator, so we could just write that as 6 over x. Okay. Or you could do 6 times 1 over x, whatever works best for you so that you could see that's just the derivative of natural log of x. This one we're going to have 9. It's going to be derivative of natural log 1 over x plus 5. And again, you could think, well, don't we have to use the chain rule? Yes, we do, but what's the derivative of x plus 5? It's just 1, so when you multiply by 1, it doesn't show up anyway. We're multiplying by 9. Again, you could put it out front, or you could just say, well, it belongs up at the numerator. So that one's all good. And the last one, we're going to have 1 over all this inside stuff, so that always happens. So whatever's inside goes in the denominator. The 10, yes, it will be up there, but before we put that, well, I guess we could go ahead and do that. And then we have to remember to take the chain rule. So what's the derivative of x to the third? 3x squared. Derivative of 1 is 0, so that's what it is. So we could rewrite this as 30x squared, right, over x cubed. And that's our derivative. That's the derivative of what it is. Again, if we tried it with maybe trying the chain rule, we could have it in a different form, but the function would have basically be the same algebraically. But this is what they're looking for you to do. So I might just, this would become 30x squared over x. I guess we can go up a little bit. Okay. Two more to go. So here's one inverse trig function. Again, it comes, this is question 35 from the review. So the only real new part, so we have a product rule here because we've got a function in the front and this function. We just need to remember what is the derivative of inverse tangent. It's 1 over 1 plus x squared, I think, no square root. And again, it's always good to come back here. Yes, indeed, it is 1 over 1 plus x squared. So it's one of those things where you'll remember best if you kind of just have it sitting next to you and you push yourself a little bit and try to, what is it? And then you check it. And you've seen me do it before. If I don't check myself, sometimes I remember things wrong, and so then you just sort of, it messes it up. So if you check yourself as you go, eventually you'll stop making, well, you might stop making mistakes. It's hard to unlearn wrong things that you learn, or things that you've memorized wrong. I've got enough things that I memorized wrong that I still have difficulties. So we're going to take this derivative. And again, the first one's always the easy part. Just take the derivative of the first function, because we've got a product rule here, right? We're going to get the something plus something. So the first part we're going to get 2x squared. The 2 comes down, so we're going to have 4x to the first power. That's that derivative. And then we just rewrite inverse tangent because we didn't do anything to it. That's the product rule thing. Now we get to take the derivative of the second part with the first part unchanged, and I like, okay, since we're not going to do anything to it, let's just put my 2x squared there so I remember not to do anything to it. And then now, what's the derivative of inverse tangent? It's 1 over 1 plus x squared, or 1 plus input squared, right? And what's our input? 8x squared. So that's the inverse derivative part. But that's the outside function. Do we need to use the chain rule? Yeah, because the input 8x squared is more than just an x. So then we multiply by the derivative of the input. So we're going to need to multiply by, the 2 comes down, so we're taking the derivative, I'll do it over here, 8x squared. Derivative is going to give us 16x, right? So I kind of show where that came from. And that goes up in the numerator. So now we just have some maybe cleaning up to do. Let's see, yeah. I think that's all I got to do. So we get, the first part's real nice and clean. Yeah. Tan inverse of 8x squared. Plus, so we've got 2x squared here, we've got 16x over here. So how about 32x to the third in the numerator, because they're going to multiply on both sides, all over 1 plus 8x squared.
Oh, where do you get the plus 2x squared?
The 2x squared comes from the first, it's the product rule.
Oh,
right? Because it's 2x squared. When I take the derivative of the second part, I don't do anything to it, but it does tag along for the ride. It multiplies. Yeah, so remember, that's sometimes, you'll get all the complicated parts, like you'll be able to do the inverse tangent, but then you forget about the template of how a product rule ends up looking. The good news is that's where the multiple choice can be helpful. It can also be unhelpful because that might be, they figure, oh, people are going to do that, so they'll put that as a right answer. And if you do that, so just check yourself. Just because your answer's there doesn't mean it's right. A lot of times these other professors, they know the kind of what wrong answers are going to look like, so they put some of those to steer you aside. Okay, is that good?
Wouldn't 8x squared be squared? Like 64x to the fourth?
Where did I?
Because the formula is 1 over 1 plus x squared.
Oh, thank you. Yeah. See? Yeah, good. I'm glad. Anyone else catch this? Right. So let's back up a space here. That's I wasn't looking right from. So this is the input. It's the input squared. So you caught me on that. See, I was almost, because I saw the x squared and I thought, oh, I'm done. No, it's 8x squared. Okay. And so let's back up here. Thank you. So when we square it, 8 becomes 64, because 8 times 8, x squared becomes x to the fourth. And that's where I mean is this exponent rules, right? Because 2 times 2, you multiply exponent to an exponent. So you'll have to use these. Thank you. Yeah. Now we're good. Okay. Last one, and we're just right on time. Questions? And actually, I'm going to rewrite that. And see, what I failed to do is follow my own advice. I said, to help me remember things, I would say, okay, I know that's what the derivative's going to be. If I would have wrote it down, I probably would have been more likely to make sure I got that squared in there. Because once I wrote it, I saw the x squared, and I thought, okay, that's all. But no, x squared is getting plugged into a square. So, thank you, guys. All right, let's look at the last one, and then we'll adjourn to office hours for anyone who wants more. So this is using L'Hopital's rule. I took this one from the homework. The ones in the reviews, they're good, but I wanted to look at this particular type of an example because it takes, as we're going to see, it takes more than one application of L'Hopital's rule. Right? They don't give us the easy ones for the test, they give us the hard ones. So be ready to apply the rule twice. And we can kind of see, because we've got an x squared, remember the way L'Hopital's rule works is as you take the derivative, you sort of get a constant for one part of it. And so we can see x squared is going to take us 2 derivatives to get a constant with that. E to the x will never get a constant, right? Because it's its own derivative. It never disappears when you take its derivative. So we're just going to have to see what happens here. So first of all, first step is to check what happens. And so we do put the limit as x goes to infinity of 5x squared e to the 4x. And what I do is I just, this is not really, nobody else does this, but I just kind of plug in infinity. Again, it's not a number, but if you take infinity and square it, what happens to it? It gets even bigger. Infinity, it's huge. What if you put infinity as an exponent on e? 4 times that, it's huge. E to the, so just remember what happens when x gets really big. E to the x gets really big. So this is going to be our case of it. It goes to infinity over infinity. So we evaluate them separately. But the thing is what's happening is this might have a slightly different limit because one might go to infinity faster than the other. And it's hard to kind of, you can't really see that. Well, I don't know, maybe you could see it in a graph. You could probably graph it and that might help. But as we're going to see, this has a different limit than infinity over infinity. So it means that, yeah, ones that they're going at different rates, And so it has a different effect. So what do? We take the first derivative. Derivative of 5x squared is going to be 10x, right? Subtract 1 from the exponent. What's the derivative of e to the 4x? It's e to the 4x, because e to the x is its own derivative. But using the chain rule, we take the derivative of 4x is 4. It's not really important because that's still, we'll still be fine, but you should show that. That's the derivative of e to the 4x is 4e to the 4x. So again, it never breaks down. So we test it again, right? We're going to say, well, what's the limit as x goes to infinity now? And right? What's 10 times infinity? 10 times is big, so it's still infinity. And e to the 4x is, again, it's still going to infinity. We haven't changed that behavior. So we're still have an indeterminate form. Use the L'Hopital's rule again, but again, be ready to, write it out and show it.
How do you derivative e to the 4x?
E to the 4x is an application of the chain rule. So we know that the derivative of e to the x equals e to the x. I think earlier in the book they use a letter u, and they say, well, e to some other function, when you take its derivative, it's going to be e to the u times the derivative of u. Oh, wait. That doesn't belong there. So what we're doing is, so e to the 4x is its own derivative, and then when we take the derivative of the exponent, derivative of 4x is 4, and that multiplies in front, not up in the exponent, down in front. Good. So let's do this again, and you'll see we're going to get something else, right? Derivative of 10x is 10. Derivative of 4e to the 4x is now going to be e to the 4x with another 4 coming down, so we get 4 times 4 in front, so 16. And again, now let's check the limit. So this was the second derivative. We can check the limit as x goes to infinity. Well, what happens to 10 as x goes to infinity? It stays at 10 because it's a constant, right? So, we don't have L'Hopital's rule to apply again, but what happens to 16e to the 4x? It goes to infinity, but now we don't have an indeterminate form. What is 10 over infinity?
0.
It's 0, because as the denominator gets big, we know it goes to 0. So we get to compare it to something different, not just infinity over infinity. And what this tells us is that, yes, e to the 4x is going to infinity much faster than 5x squared. And it goes so much faster that it makes the function actually end up going to 0. It's kind of Hercules power to do it all. So that's L'Hopital's rule, right? Just be willing to go through and do this. You're ready. Monday again, we'll focus. We'll go back to chapter 2, pick up those. Any other questions? But